Hello everyone. How are you guys doing today? Hi Ramesh. Assalamu alaikum. How are you? Hi Yasmin. I'm doing fine. Thank you. Thank you for asking, Fatima. I'm doing fine. Alhamdulillah. How about all of you are? How are you guys doing? I am feeling better, much better. Thank you. Yeah, I just hope it doesn't get worse. So I have seasonal allergy. When season changes from very hot to very cold to very cold, cold to very hot, I automatically start coughing. And sometimes my cough gets so bad that it stays for several months. And that time my life becomes hell. So I'm trying my best this year to stay healthy. So I'll see what happens. So, anything interesting happened to any of you since Monday? Oh, did you guys see the result of the election? How do you feel about it?
Not happy.
Expected. So, I don't know. Personally, I thought Kamala will win. I thought because actually I worked at election yesterday. So the center was working, Kamala won there, and we all thought, oh, she won. And then after going home, after I woke up this morning, my sister said, hey, did you hear the news? Trump won. I was like, seriously? Everybody thought Kamala will win yesterday. But now the whole situation changed. Well, whatever happens in our life, it happens for a good reason. So maybe we have the same president again. It might bring us something good. So stay positive. That's the only thing we can do. Be positive and wish for good things. I forgot which lecture is today. 17 or something. Anyway. So in our last class, we finished chapter 9 and we kind of rushed through talking about t-test. Well, I did that because we are going to do details work about t-test in chapter 10. So even if you missed something yesterday, I mean last class, last class, it's okay because we are gonna do very similar thing again in chapter 10. So in chapter 9, chapter 10 I did not upload yet. That's because I'm using the lecture from my last semester. So my goal was to make this lecture shorter from last semester to this semester, but I actually didn't have time to do so. So once I make my chapter 10 lecture a little bit shorter than what I right now have, I'll upload that. Okay. So in chapter 9, we are finding confidence interval. And our goal was to find out, or at least figure out as accurate information as possible about population based on observing the sample. So if sample says student, like a group of students, they study around 15 minutes per night on weekdays, our goal is to determine if we expand our sample size from a few students to the entire student body, then typically how long students study on weeknights. So since we cannot possibly get the exact answer, so we were trying to find out a possible interval that students study from this many minutes to this many minutes. So if sample told us that they studied, they usually study 15 minutes per night, and then the interval we can figure out told us that if we try to think about the population, then students study around 14 minutes to 16 minutes per night. Okay, so based on sample, we are trying to figure out the characteristic of the population. That was our goal in chapter 9. In chapter 10, we're going to do similar thing. We are going to observe sample, and based on the sample, we are going to test hypotheses about population. For example, maybe just by observing a few of my classes, I can make a hypothesis that my students, female students, work harder than male students. Okay, so that would be a hypothesis I observe by seeing my students. So one of the goal can be figuring out, can I apply this knowledge to the population? Can I say that all female students work harder than male students? Okay, so we observe a sample and we want to generalize the conclusion for population. So what we do is we make a hypothesis on population, and then we observe the sample and we see, well, based on the sample, do we have enough evidence to say that, well, this claim can be generalized for the population? So the hypothesis we actually make the hypothesis for population. We never make hypothesis for sample. We make the hypothesis for population because our goal is to see what population have, not what sample have, because you can observe what sample have, but we don't have any idea what population have. So based on sample, we make the prediction for population. So hypothesis, if you use an I, it means a single thing. But if you use an E between the two S, then it means a plural. So in science, hypothesis with I is a proposed explanation. And we can formally make a definition of hypothesis. It's a claim or statement about the value of a single population characteristic or the values of several population characteristics. So we make the hypothesis for the population because we want to know about the population. And we don't have to use statement to make hypothesis. We can convert our statement mathematically into numbers and symbols to represent our hypothesis. For example, we may say that typically an email has average 1,000 characters. Okay, not 1,000 words, 1,000 characters. Means every space or comma or period, all those counts. So usually an email has 1,000 characters. So see, we claim that usually email has an average 1,000 character. So we did not make this claim based on just a few samples. We want to see if this claim is true for all types of email, not only one email, but for all types of email. So here we are working with population characteristic. So average here doesn't represent X bar because we did not work with a sample. So X bar doesn't make sense here. So that this average we convert into a mu. So average 1,000 characters an email has. This is same as we are saying that mu is 1,000. So mu is the mean number of characters in an email. Or on average, 1% of the emails are undeliverable. See here, we do not have any sample to work with. So on average, we cannot say, well, it's p hat. Here, average means p. And you may wonder why I'm not using mu, why I'm using p. Well, anytime you're working with a fraction or percentage, it means you're working with a proportion. So proportion is represented by the symbol p for population or p hat for sample. So 1% means it's a proportion of all emails, 1% of all emails, it's 1 out of 100. So it's a proportion. So we are using P for that. So anytime we make our hypothesis, we must use the parameter for population. We can never use anything for sample. For example, we cannot say X bar is 1,000, or we cannot say P hat is 1%. So our claim must be always based on population, for population, not for sample. So hypothesis testing is a test procedure that uses sample data to decide between two competing claims about the population characteristic. And one of the example is, again, the one we just used is mu equals 1,000. That is one claim. Now we may have other claims based on this claim. We can say, well, mu is not 1,000. It means, nope, we don't have on average 1,000 characters in an email. Or we may say mu is bigger than 1,000. Means, well, we may have not 1,000, but more than 1,000 characters. Or less than 1,000 characters. So all of these are hypotheses. And to test the hypothesis, we compare two things. Here we are comparing mu, means population mean, with the 1,000. So we are saying, well, this is either 1,000 or not 1,000 or bigger than 1,000 or less than 1,000. Now, when you do hypothesis testing, first you have to make two hypotheses. One is a null hypothesis and one is the alternative hypothesis. A null hypothesis is a claim about population characteristic that is initially assumed to be true. For example, here, we assumed that an email on average has 1,000 characters. So that claim is for population. So mu is 1,000. We believed it to be true initially. On the other hand, alternative hypothesis is if the null hypothesis is not true, then what could be true? Okay, so if we believe that email has 1,000 characters, and if other person doesn't believe that, that means he has other belief. So for his belief, he have three choices. He may believe that, oh, we don't have 1,000 characters, or he can believe that we have more than 1,000 characters, or he can believe that we have less than 1,000 characters. So by default, whatever you believe, that's the null hypothesis. And whatever you claim, whatever you want to believe, is that's the alternative hypothesis, or whatever you want to see if true or not. And when we do the hypothesis testing, we get two types of results. Either we reject the null hypothesis, or we fail to reject the null hypothesis. All of this, the decision depends on the evidence we have. So when you carry out a hypothesis test, we compare null hypothesis with alternative hypothesis. The null hypothesis will be rejected in favor of alternative hypothesis if the sample we are working with provides convincing evidence that null hypothesis is false. So if the sample gives us enough information, enough evidence to prove that our null hypothesis is false, then we say we reject the null hypothesis, and we have sufficient evidence at that given significance level to support our claim. So here, significance level is very important because your claim either can be rejected or not rejected based on your significance level. And if the sample doesn't give us enough information to reject the null hypothesis, then we say, well, we failed to reject the null hypothesis, and that's why we don't have enough evidence at that given significance level to support the claim we are claiming. So when we state our conclusion, that's how we're supposed to conclude. Either we fail to reject. If we fail, that means we don't have enough evidence at that given significant level to support our alternative claim. And if we do reject the null hypothesis, that means we have enough evidence to support our claim at that given significance level. So yeah, Shian, I didn't post the slides because I'm still in the process of making it. So once I'm done making all the slides, I'm gonna post them. Okay, few examples about null and alternative hypothesis. Did you ever hear the expression that nobody is guilty until proven? Did you hear that phrase? So in that phrase, we said nobody is guilty. So by default, nobody is guilty. So if you want to make a hypothesis, our null hypothesis will be assuming that whoever person is charged of some crime, he is not guilty. Okay, he's innocent. That is by default what we believe. Alternative has three choices. So in here, actually, alternative has only one choice. He is guilty. So here, we don't have three choices for alternative. We have only one choice. If he's not innocent, then he must be guilty. Or in a true-false exam, by default, we believe everything is true. Okay. So when someone speak to you about something, like if you hear any gossip, okay, so by default, we assume our gossip is true, okay? And our alternative could be, well, it's not true. So we have only two choices, true, false exam. Either it's true, and if it's not true, then it must be false. So alternative is false, and null hypothesis is true. Another example, the mean age of parents at a hospital is more than 60 years. The mean age of parents at a hospital is more than 60 years. Well, this example is kind of vague, I would say. It's because it didn't say about parents of what. Parents are they working, or parents go visit, or what. But anyway, that's not the concern. The main thing is it says something is more than 60. So by default, we said, well, the mean age is 60. So mu is 60. And we are claiming that nope, it's not 60, it's more than 60. So mu is bigger than 60. So alternative hypothesis, in this class, we are going to always use equal sign for that. So either mu or p, those will be equals to some number. And alternative will have three choices, and it's not equal, or bigger than, or less than. Here it says more than 60, it means it's bigger than 60. So anytime we have more than or less than a number, we do a right tail test. You may wonder, what is right tail? Think about our car. Okay, so more than 60 means we are doing a right tail test. This is what it means. So a significance level alpha, what will be given to us, it's one-tailed alpha. One-tail means in our car, we have only one side to observe for alpha. So another claim is the mean age of the parents is less than 60. So since it's less than, so this is also one tail. So it's in the left tail. Less than means on the left side of the car. And it's one tail because we have only one side to work with. And we have the last one is says the average number of emergency room admissions per day differs from 20. So that's the claim, that it's different than 20. So different, it didn't tell us how different. Is it more than 20 or is it less than 20? Since they did not mention that, so we have two choices. Either it's less than 20 or it's more than 20. So that's why this is called two-tailed test. So when we test a hypothesis, we need either a Z or a T. So for two-tailed, whatever significance level is given, we take half of that. That's because we have twice given the information, but we only know once. So in general, the null hypothesis has equal sign, and we always say population characteristic, like either mu or p is equals to some number. And that number, we call them hypothesized value, and it's based on population observation. Okay, so we observe, we want to claim that about the population. There are three options for alternative, either not equal, less than, or bigger than, and we do the same thing, a population characteristic with some hypothesized value. And when the null hypothesis is rejected, it's not rejected just because we don't reject the null hypothesis. It doesn't mean that we have strong support to, we have enough. It doesn't mean we strongly support the null hypothesis, okay? It simply means that there is not convincing evidence against it. Our sample, what we worked with, didn't give us enough evidence to not reject the null hypothesis. So when we work with hypotheses, we face two problems. And we call them type 1 error and type 2 error. Type 1 error, it means we are rejecting the null when actually it's true. So something true, but we are rejecting it. This is called type 1 error. And we are rejecting it because the evidence we got, it's false. Type 2 error is we fail to reject the null hypothesis when it's actually false. So something is false, but we say it's true because the evidence we see thinks it's true. Example. So like I said before, everybody is innocent until proven guilty. Okay, that's the phrase we use. So our null hypothesis is that person is not guilty. He's innocent. Now type 1 error will be he is null hypothesis is man innocent, alternative hypothesis guilty. So type 1 error is rejecting the null when it's true. Okay, so this man is actually innocent, but somehow with false evidence, we said, well, he's guilty. So we convict an innocent man. That's the type 1 error. He is innocent, but we are punishing him based on false evidence. Type 2 error is that man we believed to be innocent, actually he's guilty, but we did not have enough evidence to prove his guiltiness, so we are letting him free. So letting a guilty man free is type 2 error. And that by alpha, and the probability of making type 2 error, we denote that by beta. Well, in this class, we're not going to learn details about alpha or beta or type 1 error or type 2 error. I'm just introducing you to them because there are some multiple choice questions, I think, on your homework. So if you have idea what they're talking about, you can answer them honestly. Any question about anything we talked about so far? No question? Okay. So large sample hypothesis test for population proportion. Test statistic. In order to work with the evidence, we need to know what is test statistic, what is critical value, what is p-value, what is alpha, all those things. So test statistic is a value calculated using sample data. It is the value used to make the decision to reject or fail to reject null hypothesis. In other words, test statistic is a number, and that number we calculate using a formula. And that formula, in order to calculate the formula, we need the information from the sample and also population. P-value, or the observed significance level, is a measure of inconsistency between the hypothesized value of a population characteristic and the observed sample. So what we seen by observing sample and what we assume about the population, that difference is the p-value. A decision as to whether null hypothesis should be rejected or not, we use two types of methods. In one method, we compare p-value with the chosen alpha value. So we compare them. If the p-value is smaller or equal to alpha, then we reject null hypothesis. But if the p-value is bigger than alpha, then we fail to reject the null hypothesis. I forgot to mention something. Here. The information you learned from here, I'm gonna ask true, false, fill in the blank, those questions from here. For example, I can ask, well, is this a valid hypothesis? X bar is 1,000 or P hat is 1,000. Of course, it's not valid because X bar and P hat cannot be used in a hypothesis. Hypothesis always has to be based on population characteristic, not sample. And here, the information you learn from here, I'll ask that in the exam. Also, type 1 error and type 2 error here. What is type 1 error and what is type 2 error? I'm going to ask you. So you're going to say, oh, type 1 error is rejecting the null hypothesis, one is true. And type 2 is failed to reject the null hypothesis, one is actually false. Exam 2 will be based on chapter 9, 10, 11, and probably 12. 19, 11 for sure. But 12, I'm not sure yet. And this example is interesting. So I may ask about this example. The probability, you can ignore. But I'm going to ask this. So we compare P with alpha, and if P is bigger, we fail to reject the null. And if P is smaller or equal to alpha, then we reject the null. So this is one method. So in this method, we need to know what is p-value. Alpha will always be given. Okay, either alpha will be given or confidence level will be given. Like they will say 95% confidence. With 95% confidence, prove that this claims true or false. Okay, so either confidence level will be given or alpha will be given. But p-value we have to calculate. And finding p-value is kind of not too good. P-value doesn't always give us the exact number. Sometimes we have to make an estimation about the p-value. So that's why p-value, even though it gives us more accurate result about a hypothesis test, but personally, I prefer the second method. In the second method, we calculate the test statistic using a formula, and we get the critical value from the table. So if you're working with Z, we use the Z table to get the Z value, If we're working with t, we get the t critical value from the table. So one value we get from the table, we call it critical value. And one value we calculate using a formula, we call it test statistic. And we compare them. If the table value is smaller or equal, we reject the null. But if the table value is bigger than the calculated value, which is the test statistic, then you fail to reject the null. And this is my favorite method, because in this method, the two numbers we are working with is easy to find. One is easy to find from the table, and the other one is using formula. So how do you find the critical value for z? So you have two choices. Either you memorize it, what? Find p1 minus alpha and z. Yeah, either you memorize it or you have to find it manually. If you want to find it manually, you're going to use alpha. So whatever we did in our last class in chapter 9, we are going to do the exact same thing. Whatever alpha you have, you subtract the alpha from 1, and then you take half of that if your sign has not equal sign. But if your sign doesn't have the equal sign, if you're one-sided, if you're doing one tail hypothesis test, you do only 1 minus alpha, and then whatever number you have, you go to the z table and see which z value has that probability. But if you are working with not equal sign, means 2 tail alpha, then you subtract 1/2 of the alpha from 1, and you go to the z table and see which z value has that probability. Or you simply have this in a cheat sheet. So when you do the hypothesis testing, the 3 most commonly used alpha is 0.1, 0.01, or 0.05. These are the most used alpha level for hypothesis testing. If you're doing one tail, then for alpha 0.1, your z value is 1.28. But if you're doing two-tailed, then your alpha level is, for alpha level 0.1, your z value is 1.645. So one tail means, oops, you have mu bigger than or less than your hypothesized value. Okay, so if your alternative hypothesis has this, then this is one tail alpha. But if your alternative hypothesis has is, oops, I should write it here, has mu not equal something, that means two-tailed. So you simply see what alpha level they want you to check, or they want you to work with, and then you go and get the z from here. So this is the easy method. You simply use this. You don't have to do it manually. However, if you're working with P, then you have to do some work to find the P. So P value is the shaded part for your claim. So when you are claiming with bigger than sign, whatever area you have that is bigger than the calculated z, that part is the p-value. So calculated z, it means we need to find the test statistic, which is the calculated z. And that will give us the p-value. So how do you find the p-value for z? First, we find the test statistic using formula. What's the formula? It depends on which scenario you're working with. If you are working with proportion, then your formula is different than if you're working with mean. So whatever that is working with, you find the test statistic first, and then you go to the z table and get the probability. So that probability is under the curve from the z table. Based on the sign of the z, you get your different p-values. So if you're working with one tail hypothesis testing and you found that your z, the calculated z, has a positive sign, then your p-value is 1 minus the area you have under the curve for that z. But if your z value has a negative sign, then your p-value is the same number you have from the table. For two tail, it's twice whatever you are doing in one tail. And if your z has a number that is bigger than 4 or smaller than -4, then automatically your p-value is 0. Okay, so this is the rule. So you don't have to memorize anything. All you have to do is make sure you write down everything in your cheat sheet. As long as you make your cheat sheet very well organized with full of important information, then you'll be fine. Okay, so here are some examples. Let's say you calculated a z and you found your z value is -2. Then if you're doing one tail hypothesis testing, then your p-value will be 1 minus, no, p is negative, right? So we take the exact number from the z table. So you go to the z table and see what's the area we have for z -2. And if you're doing two tail, whatever area you have, you multiply that by 2. But let's say you found your z value is 2, positive number. So it's a positive number, so you subtract that from 1. And whatever you have, this is actually same as the negative value. For twice, you multiply that by 2. And you have the same thing. 0 is an interesting number. It's neither positive nor negative. So for 0, you take the exact same number. For either for one tail, you take the exact same number. And for two tail, you don't multiply that by 2. 0.5 times 2 should give you 0.5 times 2 is 10. Oh yeah, you multiply by 2, you get 1. Never mind, yeah. So for 0, it's same thing. For one tail, multiply 2 means you get 1 for two tail. Personally, I don't like this test, p-value test. I like the test statistic test. So here are some examples. If you want to do it, I will give you 1 minute to find the p-value for these given z-values. And if you're lazy, then I will simply show you the answer. What do you prefer? Try it on your own, or you just want me to go over the answer? You are finding the p-value based on these z-values. That means you need a z-table. Okay, I'm too lazy to do it. So I'm going to simply show you the solution. For the first one, ours is positive 1.6. So we go to the table and see the area for z 1.46 is 0.9452. Since it's a positive z, so for that, we have to subtract it from 1. And our answer is 0.0 5 for it. Or you can actually simply go to negative 1.6 and that's your answer. On the other hand, for B, ours is negative 117. So we directly go to the z table and the number we have there, we take it and that's our answer. That's it. Any question? No. So comparing alpha with P, let's say you found if P is this, and they told you to use the alpha level 0.05. So here we can see that 0.3 is smaller than 0.5. So if P is smaller than alpha, we reject the null. On the other hand, if they wanted to work with alpha 0.01, now for alpha 0.01, our P 10352. So now our P is bigger. When P is bigger than alpha, we fail to reject the null. Okay. P is smaller or equal means we reject the null. Means whatever we initially believed, we don't have enough evidence to reject that. We keep it. And if P is bigger, then we fail to reject the null. It means whatever we are initially believing, we keep it because we don't have enough evidence to reject that. Here we have an example, compare P with alpha. And again, I'll give you 1 minute and figure out in all 3 scenarios, do you reject the null or do you fail to reject the null by comparing p-value with alpha? If you want, you can write down the answer on the chat box. What do you think about ABC? In A, do you reject or fail to reject? Null hypothesis. In B, do you reject or fail to reject the null hypothesis?
For A, I say rejected, and
Reject.
for B, I said failed to reject,
Fail.
and for the last one will be rejected as well.
Rejected. Any rejection about these answers from anyone? Anybody disagree with her? Does anybody agree with her? Or all of you just don't care? Well, you may not care now, no problem. But in the exam, you must care. Otherwise, you're not gonna get points. So let's see how B feels. Let's see A. A, we have 0.024. Let me write one below another one. So we have 0.05. Our P is smaller than alpha. We reject. In here, our alpha is 0.001. So our P is bigger than alpha, right? 0.009 is bigger than 0.001. So we fail to reject. this one, we have 0.05. Guess what? If you round this, it will become 5. So the condition says if P is smaller or equal, then we reject. So yep, she is perfect. She did them wonderfully. Yusuf, it's okay. We all can't count at some points in our life, especially if you work with decimal and negative numbers. Okay, now we are going for the hypothesis test. How do we actually do hypothesis testing? And in the first part, we are working with proportion, and in the second part, we are going to work with mean. So how do we do hypothesis testing for population proportion? Since you're working with proportion, that means first step is find out what proportion you're working with. So from the given scenario, so in our scenario, a sample will be given, and among all the people we have in the sample, there will be a certain number of people share the same characteristic. So from these two numbers, we will calculate the p-hat. P-hat means the sample proportion. It means from all the people we have in the sample, how many people share the same property. We're going to calculate that. Then we set up a hypothesis. Since you're working with proportion, so a hypothesis must have to have P, which is the population proportion. Now, there are 3 things we're supposed to check, but actually we don't check them here because by default, we assume all the assumptions are true. Now, the 3 assumptions in real life we're supposed to check is that the p-hat, the sample proportion, the sample you worked with actually drawn from a random sample. B, we need to check that the sample size is large enough. So n times the hypothesized value should be at least 10, and n times 1 minus hypothesized value should be at least 10. And the sample you're working with, it can't be, the size of the sample can't be more than 10% of the population size. So these are the 3 things we're supposed to check in real life. But in this class, we just ignore them because by default, we assume all these things are true. So in real life, when you check all of these, then we go to the next step. We find the test statistic. Anytime we are working with proportion, we must find the z statistic. So z statistic has the formula p-hat minus hypothesized value. We divide that by hypothesized value times 1 minus that divided by n, everything under the square root. In other words, it's p-hat minus p. We're dividing by square root of p1 minus p over n. Okay, so that's the formula. So p is the hypothesized value. It means what number we get from population. P-hat is what we get from sample. So we use both of them, we get a z number. Now, if you're using p-value method, that means you're going to go to the table and you get the area. And you're going to compare that with alpha. But if you're working with critical value, so we are going to find critical value. Wait, find the p-value using the z statistic, or find the critical value from the table. And compare the p-value with the alpha or test statistic with the critical value. So either you go and get the p-value or you go and get the critical value. So go for one of them. If you use p-value, that means you have to compare that with alpha. But if you found a critical value, you're going to compare the critical value with the test statistic you found in this step. Based on the results, the comparison you do, we either reject the null or we fail to reject the null. So we decide what do we have. Once we decide, then we make a statement about the conclusion. What conclusion we come up with. Any questions so far? Okay, so let's apply all these steps in one question. It says, in a survey of 1,000 women from age 22 to 35 who work full-time, 560 of them indicated that they would be willing to give up some of their personal time in order to make extra money. In other words, people who work full-time, especially the women from 20 to 35 years old working women, they asked 1,000 of them, are you willing to give up your free time to earn some extra money? 560 of them said, yep, we would gladly give up our time to make some extra money. Now, based on the sample we just worked with, our goal is to figure out if the majority in that age group will be willing to give up their extra time, give up their free time for extra money. Any question about the scenario? What is given and what is our goal? Any question from anyone? Remember, in statistics, the hardest part is figuring out what is given and what they want you to find. So if you're an expert figuring those two out, you will be fine in stat class. So we observed some working women and we figured out that a certain amount said they would do anything. Now, based on that 1,000 people, can you generalize the statement that, well, more than half of working women will be willing to give up their free time to earn cash? So here, they're only telling us that the sample you're working with is drawn from a random sample. Okay, so the last line means that thing. It means the three conditions are satisfied here. Okay, now they want us to do a hypothesis test at the alpha level 0.01. It means with 99% confident, can you claim that majority of the women are willing to give up their free time to earn money? So we start by making a hypothesis, and every hypothesis is for population. So we do null hypothesis and alternative hypothesis. before even making out null hypothesis, whatever claim we are claiming, that gives us the alternative hypothesis. What's wrong with my pen? It's working now. So our claim is majority of the women are willing to give up their time. That's the claim. So majority of the women, and here we have 1000 over 560. That means we are working with a proportion. For p hat, the samples, we have 560 over 1000. So our claim has to have the population proportion. Since we are given the sample proportion, that means our hypothesis will be based on population proportion. Now, majority of the women are willing to give up their time. Majority of women. How can you symbolize that? Majority of women. I already gave you a hint. Majority of women means more than half. So majority of women are willing to give up their time. How can you write this? Any idea? Symbolically, it's symbols. How can you write majority of the women? Or simply majority? Any idea from anyone? Nobody has any idea? Seriously? Okay, think about this. Majority of my students passed this class in the last exam. Fatima, you're very close. Greater than. Equal doesn't make sense here because majority means more than. So it's more than. How can we symbolize majority? By which number? One. How can you answer this? Majority of my students passed the last exam. So if you want to say this to someone else, how are you going to express that? How are you going to restate this? Restate that statement, Yusuf? Or let's say majority means most, right? So most of the students passed. How can you say this mathematically? No, 560 is simple, but we are thinking about population. The student. What is there any number for the students? Wonderful, Ramesh. See, anytime we use the word majority or most, it means our middle point. It's more than our middle point. So what is our middle point? 50%. So majority means it's more than 50%. So when I say most of my students passed the last exam, it means our passing grade is more than 50%, right? How do we visualize majority? It means it's more than 50%. So 50% is our cutting point always. Among whatever we have, majority is connected with 50%. So majority of the women are willing to give up their time. It means the proportion of the women that are willing to give up their time is more than 50%. But we actually don't use percentage in here. So instead of percentage, we write P is bigger than 0.5. So our null hypothesis by default has always the equal sign. So P equals the 50%. It means, well, 50% of the working women are willing to give up their time, free time. So P equals 0.5. Majority, this is from your homework, okay? So you're going to do this type of question in the homework. Anytime, usually they give us a number for population. When they don't give us a number for population, they are, of course, will give you some hints. So based on the hint, you figure out what is the number they're giving us. So this 0.5 is the hypothesized value. Hypothesized value. So whatever number we get based on the population is the hypothesized value. So step 1, we state our claim. Step 2, we find out our proportion for the sample. So sample proportion is 560 over 1000. In other words, 0.56. In third step, we need to check the 3 assumptions, but we're not going to do it here. We are going to go to the next step directly. We are finding the Z statistic. So Z statistic, it means we are finding the number using a formula. So Z statistic for proportion, the formula is P hat minus P, P1 minus P over N, everything is under the square root. So 0.56 the hypothesized value they're telling us here are P. This is the same P. It's 0.5. So we have 0.5. 1 minus 0.5 is another 0.5. And the total people in the sample is 1000. Oh, actually, I should highlight this. Everything is under the square root. All of you should try this in the calculator, because trust me, in the exam, most of you will make a mistake. So try this. This is a very important number. What number you get by by plugging all of these in the calculator. Wow, Elise is fast. 3.794. Let me keep to 2 places because this is Z, and Z table has 2 places after the decimal. So 3.79. So this is our Z statistic. Now, if you want to, and this is a positive number, okay? So if you want to work with p-value, then our p-value is either negative z, or whatever you got from step 3, or it's 1 minus z, whatever you got there. You get the same result. So not z, it's the probability of z. So I shouldn't use z. I should do this. It's 1 minus probability of z equals 3.79, or it's simply probability of z equals negative 3.79. You're gonna get the same thing. So let's go to the z table and see what do we have. Z. 3.79 for negative 3.79, negative 3.7. Oh, it's not top, I forgot. Negative 3.7 is here, and our 9 is, oops, I need more place. Our 9 is here. Negative 3.79. Negative 3.79. Let's see what is positive 1. 3.79. 9 is the last one. So 3.7, and our last one, 3.7 is here, and our last one is here. So 1, 2, 3, 4, 4, 9. So 1 minus 1, 2, 3, 4, 9, 2. 10 minus 2 is 8. 0, 0, 0, 0. No, 3, 0. 1, 2, 3, 0. And what do we have here? Negative 3.7, 1, 2, 3, 4. Yeah, the same thing. 1, 2, 3, 4. Oh, sorry. It's a bigger than sign. So for, oh no, 1 tail. Yeah, 1 tail is fine. Never mind. Ah, I hate that. So this is the p-value we have. And if you observe the alpha they gave us 0.01. Okay. So you compare p with alpha. So this is called carry out the hypothesis test. It means compare your alpha with the p. So what do you observe? P is bigger than or less than alpha, which one? Of course, less than, right? P is way smaller than alpha. So when P is less than alpha, what conclusion you make? Do you reject the null, or do you fail to reject the null? We reject the null. Reject the null means we're rejecting that P is 0.5. So we are rejecting P is 0.5. This is what rejecting the null means. So that's how we do, that's what you do when you work with p-value. But let's say when you work with c-value, it's the p-value. So if you want to work with Z value or Z critical, to find the Z critical value, you look at alpha. Our alpha is 0.01. And do you remember the table I gave you? So we have one tail test. We have one tail test because it's one-sided symbol. So alpha 0.01 and it's one tail test. Alpha 0.01 with one tail test. Look at here. One tail Z for 0.01, it's 2.33. So you need to do all those math. We simply come to this table and use it, and I see that the critical value we have is 2.33. So when you carry out the test, we look at the Z statistic versus Z critical. Our Z statistic was 3.79. Oh, when you do this, we have to look at their so critical is always positive. No, mind. Oh no, not always positive. We look at their positive things. We ignore their signs. So we found our Z was 3.79, and we found our Z critical on the table is 2.33. So Z statistic is bigger. When Z statistic is bigger or equal than critical, we fail to reject the null. Sorry, my bad. We reject the null. Z critical is smaller, so we reject the null. See, we came up with the same conclusion. We are rejecting the null. So we did all of this. Now the last step is make your conclusion. When you reject the null, what happens? Why do you care? What conclusion we have? That's the last step. So I'm too lazy to write this down. Instead, I'm going to just show you the answer. When we reject the null, we conclude that the sample does provide convincing evidence that the majority of the women, the working women from this age to this age, they're willing to give up their personal time for money. Okay. In other words, we have enough evidence to support our claim at the alpha level 0.01. So when you make a conclusion, you must make a conclusion. In the exam, it's 2 points. So rejecting the null means we have enough evidence to support our claim at the given alpha level. These three things are the most important thing. We have convincing evidence. So we have convincing evidence to support the claim at this level. Claim means whatever claim we have in our alternative. Okay. So we are done with proportion. In our next class, we are going to work with mean. And I'm going to do a few examples and it will be done in chapter 10. Then go to chapter 11 in our next class. Next class. Any question from anyone before you go? Any comments? Any concern? Once I'm done making my slides, I'm going to post them on Blackboard. And I'll do it over the weekend. Not tonight or not tomorrow, but over the weekend. Okay. And whoever stayed, thank you so much. One thing I observed is that during exam, All of you want to use extra time. It doesn't matter how many times I tell you that the class is over, you have to leave now. Nobody listens, everyone to stay. But during lecture, even 1 second after our class is over, they don't want to stay. So I'm really angry now. Almost half of you left the classroom because I'm over 5 minutes. Haha. So let's see who stayed. I can give you extra time during your next exam. Ellison, Fatima, Laila, Miyako, Queenie, Rami, Salma, Tao, Wendy, Yasmin, Oasis, Yusuf. Okay, great. Wonderful. Thank you guys. Have a wonderful weekend. Have a good night.
Have a good
And
night.
see you again on Monday. Bye-bye.